Hi all, let's continue our discussion on chemical equilibrium. And there are two variables, or not variables, but two quantities that I want to discuss in this video. That's the reaction quotient, which is QC, and the equilibrium constant, which typically is indicated as Kc. The first quantity I want to discuss is this reaction quotient. And that's indicated by the letter Q. But it's going to be based off of concentration, so many times people put a subscript C. I want to remind ourselves about equilibrium, in particular dynamic equilibrium, from a reaction that we saw in a previous video. You have this equilibrium arrow, and you create 2 moles of HI per reaction. And we had something like this, where you have T, we have concentration, and H2 I had pretty high initially, and it drops as the reaction proceeds. Concentration of H2. We had a concentration of I2, which was a little less at the beginning, and it also drops because it is a reactant. I2. And we started with 0 amount of the product, and it rises as the reaction progresses. And it looks like here we have a lot more HI at the end than we do of the 2 reactants. 0, 0. Okay. We discussed that the reaction reached equilibrium around this point where the concentration started to become steady or plateau. Let's just call this at equilibrium now. Let's drop the word dynamic. I think we understand now that equilibrium means that the concentrations are constant, but the reaction is still going in the forward direction and the backwards direction. It's just that the net effect, there is no net effect on the concentration. We describe this point, or this time before equilibrium, as pre-equilibrium. So what is reaction quotient? Reaction quotient is just a way to describe the concentrations at any time. That's important. So QC is a way to describe or quantify the concentrations of reactants and products, just shorthanding that, at any time. That is the important part. At any time. Now it's changing. For instance, very early in the reaction, we have much more H2 and I2 versus HI. So for instance, at this point, maybe right here, we have a concentration here, a concentration here, and a concentration there, those 3 circles. You could have a Q for this time point, you could have a Q for this time point, you have a Q for this time point, etc. So at any time you choose. Okay, so let's say at time equals, let's just estimate. I have no idea. This could be an hour, this could be 400 days, but let's say at time equals 30 seconds. We have an H2 concentration equal to, let's say, 0.46 molar. We have an I2 concentration of 0.38 molar, and we have a concentration of HI equal to, I'm just making up these numbers, but I'm making sure that the order's the same as what the graph is telling me. So HI is the least. Whoops, you can see that. HI is the least. We'll call that 0.19 molar. Okay. What is Q? Q, or QC, equals the concentration of the products over the concentration of the reactants. So the products are HI. There's only one product actually. And then we have the two reactants, H2 and I2. And again, this will change depending on what time point you're looking at. But we could always think of QC as products of reactants. There's one last twist, that you have to use the coefficients. In the kinetics unit, we rarely use the coefficients. Here we do. So that 2 acts as an exponent in our reaction quotient, and you would square the HI. The coefficient for H2 and I2 was 1, so there is no exponent here. Okay. So how do we generalize this? Okay. Oh, by the way, so you could figure out what is the QC at t equals 30 seconds. I'm not sure why I put that in parentheses. 30 seconds. Okay, and you can figure that out by just plugging in the numbers. But in general, if we have a reaction that's, for instance, A to the A, so that's coefficient of little a for the molecule big A, B, it's at, there's an equilibrium, or I shouldn't say there's an equilibrium, but it can go in the forward and reverse direction. And we get CC plus maybe DD. Your QC equals products over reactants. So D to the D, C to the C. I'm not sure why I put D first. Oh, that's gonna bother me a lot. Let me put C first. So that would be a D. Again, C to the C, D to the D, A, exponent A, B, exponent B. Okay. We'll put that in a box. I'm not going to explain it here, but the other thing is that these are concentrations. And we could get concentrations for something that's a gas, okay? Just take moles divided by volume, and we could get a concentration for something that's dissolved. And most likely it's going to be dissolved in water, so it's going to be aqueous. We can't really get a concentration for a pure solid, because it's not a solution, or a pure liquid. So you got to remember this one very important point. You can only use compounds that are gas or aqueous, not anything that's a solid or anything that's a liquid, pure solid or pure liquid. Just look for an S or an L. Do not use that. Not use that in the reaction quotient. Now this C, or we'll just say this QC, that is called the reaction quotient. And it's a C for concentration. In this case, it is based off of concentration. You could have a Q, a reaction quotient that's based off of pressure, because if everything is a gas, pressure is directly proportional to the concentration. But for now, let's just keep it at QC. Okay. And just remember that you could figure out the QC for any time point if you're given those concentrations, or if there's a way to get those concentrations. I'm emphasizing that QC can be at any point because now we're going to talk about KC. And KC actually is very specific. It is the reaction quotient at equilibrium. Let me write that down for us. This is part B. Let's go on to KC. Equilibrium, constant. Big K. Now, just like we had QC, you could have KC. Okay, and that is the K based off of concentration. So how should I want to say this? I'll just put a KC there. KC is actually QC when the reaction is at equilibrium. Another way you could say that is QC equals KC at equilibrium. So if you think about it, KC only applies when you're at this time or beyond this time, because that's when the concentrations are at equilibrium, that's when the concentrations are held constant. Just a little note, some textbooks use KEQ instead of QC. Some textbooks use KEQ, and that's the same as KC for us. Actually, those K's should be italicized, but I'm not going to do that if I'm writing it by longhand. KC. Okay, so let's take up another reaction. Let's take, let me find one real quick. I like this one. We'll do a couple of reactions. The first one that we're going to use to look at KC is N2 gas plus O2 gas goes to 2NO gas. And if I ask, write the equilibrium expression, your answer will be this. Kc equals the concentration of NO squared over the concentration of N2 times the concentration of O2. That's the expression. What is actually the Kc? Oh, by the way, we should specify that this is at a specific temperature, and we'll just choose at random at 25 degrees C. Because equilibrium is temperature dependent. Okay. And what does it mean? Let's say we run the experiments and we're given that Kc is equal to 4.1 times 10 to the negative 4, or negative 4. Okay? What does that mean for us? It means that when Kc is less than 1, Kc will always be positive. Okay, let's just say that off the bat. Kc is always, it's a ratio, positive. But if Kc is less than 1, which we do have here in this case, the reactants are favored. Because, this ratio is less than 1, that means that the denominator, the product of these two, is going to be larger than the numerator. And so in general, reactants, those are the reactants favored. If Kc is greater than 1, products are favored. If Kc is equal to 1, okay, then this ratio is identical, or it's the numerator and denominator is identical. We will say that reactants and products are equally favored. But what it really means is that the numerator and denominator are identical. Okay. Let me write down the general Kc equation now. Kc is concentration of C to the C, concentration of D to the D, concentration of A to the A, and the concentration of B to the B. It's the same thing as the reaction quotient, because Kc is the reaction quotient when the reaction is at equilibrium. Now, I had a couple things in mind that I wanted to add, and I forgot. Try to figure it out. Oh, yes. Kc. Obviously, that's the equilibrium constant. And C equals concentration. Later on, in future videos, we'll talk about figuring out the equilibrium constant using pressures. But for now, let's just use concentrations. I want to mention, which I didn't mention for the reaction quotient, but it's true for that also, these are unitless. They don't have any units. Unitless. That's different than little k. Little k was, what was little k? The rate constant. And it was very important for us to know the units for the rate constant. In this case, big K, you don't need to know the units. There are no units formally. Again, only use compounds that are in the gas phase or aqueous. I'm going to repeat this over and over again because this is a mistake that I sometimes make. Not if the compound is solid or liquid. So you need to know the states. They need the either you need to know the states or the phases, or the problem will give you the states or phases. Oh, that's also what I wanted to say. It's unitless, and K is temperature dependent. Temperature dependent. Okay. Thus far, in our minds, Q and Kc are the same thing. It's just where you take those measurements. Q can be at any time. Kc is Q only when the reaction is at equilibrium. So in this time period, from T equals at equilibrium and beyond, that's when you are calculating Kc. You're literally looking at the concentrations and fitting it into the equilibrium expression. The last topic I want to talk about in this video is comparison of QC and Kc. or the relationship. Simply, what we could say is, what if QC is greater than KC? Okay, because, again, this is a constant for the equilibrium expression. This one right here. That will always stay the same number regardless of how much of each you start with. The reaction will reach this Kc, this equilibrium constant. Then you can figure out, well, if we have an initial concentration, Qc, what does it mean if Qc is greater than Kc? What does it mean if Qc is less than Kc? And I think we already know what it means when Qc is equal to Kc. That means that it's at equilibrium. Means reaction is already at equilibrium. But what about these two indicators? Well, if QC is too big, bigger than KC, what that means is that let's take a look at it. We have concentration of products raised to some coefficient and concentration of reactants, products over reactants raised to some coefficient. If QC is too big, our denominator is too small. Because it's off equilibrium. The denominator is too small. The reactance is too small. The denominator is too small. Or you could think of it as the numerator is too big. That a very big numerator will give you a QC that is larger than the KC. So this situation we are describing right here. QC is too big. So it means that numerator is too big. What does that mean? It means that to get to equilibrium, we have to favor the reactants. Therefore, to get to equilibrium, the reaction has to shift temporarily, okay, until equilibrium is reached. Temporarily towards the reactants. Because QC is too big, we got to get this number, the denominator, bigger. We got to get the denominator bigger. So it temporarily shifts towards the reactants until equilibrium is reached. Okay? And then you're good. QC equals KC, and there is no shifting anymore. So it's this idea of the reaction adjusting. The reaction is adjusting to get what? To get QC equal to KC. That's the idea. Okay, so what if QC is too small? QC is too small. So QC is too small. It's lower than KC. Well, let's use this again. If QC is too small, then we need more products and we need less reactants. So again, now this situation right here is now going to be described right here. And that means that we need the reaction shifts again, this time temporarily to the products. to get QC bigger, to get QC to go up such that QC again equals to KC. All right, so it's all about getting the QC to be equal to the KC, because QC many times is going to be off equilibrium, right? These two situations describe QC that concentrations are not at equilibrium. For instance, right here, see, those concentrations at time we said 30 seconds are not the same concentrations at equilibrium. So the reaction is going to push towards the reactants to try to get the HI larger and to get the H2 and the I2 smaller. Let's add that. So these two situations, that one and that one, those are off equilibrium. They're not at equilibrium. Equilibrium is a powerful concept. Reactions go towards equilibrium, where things are at a steady state, where the concentrations remain constant. Okay? And that's why when your QC is not equal to KC, the reaction will adjust the rates of the forward and the rates of the reverse. They will adjust such that eventually QC will equal to KC. And that is the relationship. That's how we're going to use the relationship, because a typical problem is, actually I have one set up. If we have this reaction, CO grams plus Cl2, not grams, sorry, gas, goes to, in equilibrium, CO, Cl2, gas. If the equilibrium constant at a certain temperature equals 216, how, let's not say how, let's say which side is favored. Will the product side or reactant side be favored if we have a concentration of CO? So now I'm going to give us numbers. CO equal to 0.012 molar, Cl2 equal to 0.054 molar, and we do have in this example some product already equal to 0.05, is that right? O molar. Will the product side or the reaction side be favored if these are our conditions? I'm not going to do this problem with you. We're running out of time. But you would want to figure out QC, and you would decide, is that QC greater than, less than, or equal to KC? And if QC is too big, right, you need to favor the reactants. Oh, no. If QC is too big, you gotta favor the reactants. I mean, you gotta make this number bigger, the denominator bigger, to make QC smaller. Phew. But if you calculate QC to be less than KC and QC is too small, then you gotta push towards the products to get QC to be greater than KC, or QC to be equal to KC. Ugh, getting a little bit tongue-tied. Okay, so go ahead and try that problem. Solve for QC and see if it is greater than, less than, or equal to KC. And that will tell you which side is favored.